A very warm welcome to you once again. Thank you for joining us here today for Lecture 3. So last time we finished off here, we looked at wanting to cover the categories of topology. So the four most common topologies you'll come across is the mesh, the star, the bus, and the ring. So we'll speak about each of these topologies in turn. So if we look at the mesh topology, it's basically a point-to-point connection from each and every device that is involved. So you can see each and every device has a connection to every other device that is available to it. So this is a pure mesh topology. In reality, this type of topology does not exist as much. You may see a partial mesh because this type of topology is obviously very expensive to maintain if you have a connection to each and every station. So while this mesh topology overall, a full mesh topology, is not very common, but it is used in some cases, but you'll more likely come across a partial mesh topology in which the station is connected to some of the endpoints, not all necessarily to all the endpoints. In a mesh topology, as you can imagine, every device has a dedicated point-to-point link to every other device. And the term dedicated means that the link carries traffic only between the two devices it connects to. The advantage of this topology is the mesh offers several advantages over other network topologies. Basically, it does have, as you could see, dedicated links. You can see here this topology once again on the right-hand bottom corner. The dedicated links eliminates traffic problems because if it cannot find one path to any given station, it can always go to the same station using a multiple paths, right? Going through via a different station. It is pretty robust. If one link becomes unstable, it does not incapacitate the entire system, and its privacy or security is wonderful because only the intended recipient sees the local boundaries, right? Or the local boundaries, basically the physical boundaries, prevent users from gaining access. Because here, there's nobody else eavesdropping into this connection. And the point-to-point links make fault identification and fault isolation very easy. And it is able to reroute traffic to avoid links with suspected problems. So if any link has a problem, the station, as I mentioned, can send the same information, if not directly, it can send this information indirectly through other connections it has via different stations. The disadvantages of the mesh topology, as you can imagine, the main disadvantage of a mesh topology are related to the amount of cabling and the number of I/O ports required for such a cabling or such a layout to be actually implemented. Every device must be connected to every other device, so that's a lot of work, obviously, and a lot of kind of costs associated with that. And the hardware required to connect each link, which is I/O port or cable, can be prohibitively expensive. So example is a connection of a telephone regional offices in which each regional office needs to be connected to every other regional office. Okay. In today's world, the internet has some form of mesh topologies. However, it is not a full mesh topology. It will be a partial mesh topology. But in the olden days, when we had telephone regional office, there was a possibility that the offices are connected over a pure or full mesh topology. Now let's talk about the star topology. A star topology is a point-to-point topology. You can see, for example, a switch or a hub connecting to the station, right? The station has basically one connection from itself, is a point-to-point from the station itself or the device itself to the hub or the switch. So in this particular situation where you see which is the star topology, which is basically a point-to-point topology. So we had a hub or a switch there, and basically all the devices are connected. All the devices are basically connected to the central station, which is the hub or the switch. So in a star topology, each device has a dedicated point-to-point link only to a central controller, usually called a switch or a hub. Now, the devices are not directly linked to each other. So you can see the difference here, right? The devices, unlike the mesh topology where each and every device was linked to each other, devices here are not linked to each other. They are connected to a central station, which is basically the central controller or the hub or the switch in this case, right? Unlike a mesh topology, star topology does not allow direct traffic between devices. In fact, it is the controller, which in this case is the hub or the switch, acts as an exchange mechanism to transport information or transfer information from one device to another. It has to go through the hub or the switch. If one device wants to send data to another, it sends the data to the controller, which once again, as we mentioned, is the hub or the switch, which then relays the data to the other connected devices. A star topology is less expensive than a mesh topology. So looking at the advantages of what it has, right? It is less expensive than a mesh topology. In a star, each device needs only one link and one I/O port to connect it to the hub or the switch. So much less cabling is required. And if one link fails, only that link is affected. All other links remain active. Easy fault identification and fault isolation is possible, of course, because most of the hubs and switches usually will have a light indicating if there's connectivity. If there is an issue, it will either go red or no lights at all, indicating the connectivity is missing. As long as the hub or the switch is working, it can be used to monitor link problems and bypass defective links. One big disadvantage, however, of the star topology is the dependency of the whole topology on one single point, which is the hub or the switch. If the hub goes down, the whole system is dead. The star topology is very commonly used in a local area network with a central switch. In real life scenarios, which involve servers, we want to connect the servers to multiple switches to avoid a single point of failure. Now, if you look to see the practical way a server looks, I find that when I was delivering my courses, many students may have never come across the actual hardware, how that looks like. So they wanted to find out, for example, what a real server actually looks like. So this is a server, a rack server that you may find, right? Just this is a rack, which is like a pizza box. Usually it's 1U, which is about 1.75 inches, right? And basically the height is basically 1U servers. Of course, you can find servers which are 2Us, 3Us, 4Us, right? But those have become less common, and most of the time nowadays you use either a rack server or you use a blade server. I'll show you a blade server in a few slides in just a moment. But this is what a rack server looks like. So this is a 1U server, which is about 1.75 inches in height, and basically slides into the rack. Right? This is what the front view may look like, and these will be the drives that you can pop in. Usually these are what is called hot swappable drives that you can just plug in and plug out while the server is actually running. There may be some VGA ports, some external diagnostic ports that you can use. There'll be some USB ports. At the back of these servers, we'll just look at it in just a moment, what that looks like. You may have redundant power supplies. You can see here the possibility of using two power supplies. So yeah, if you ever have to order this type of servers, basically by default they'll come only with one power supply. You may want to consider for sure having a second power supply, right? So if one power supply dies, basically the second one is still functional and your server is still up and running. At the back, you'll see a lot more connectivity ports, as you can imagine here. There's a video connectivity. The VGA port is here, the USB. In some of the newer servers, you may find an HDMI ports as well. You'll have connectivity with your Ethernet as well available to you. Internally, the rack server may look something like this, right? Of course, there will be the actual CPU, right? So you can see here a couple of CPUs in here, which has the heat sink. You can see the word heat sink here. So there's heat sinks here on top of the CPU. Some will be with fans. Most of them nowadays will come without fans necessarily. And the heat sink should be good enough to cool the system down. And then there'll be a lot of slot for your RAM, right? You can see a lot of RAM slots in here. So it's a very, very compact design in which you have everything that you need within one very simple, efficient pizza box, so to speak, right? Then a more common server that you'll come across is a blade server, right? So this can be quite tall. This could be, for example, 8 U's in height, for example, right? So pretty tall. And then in here, each and every one over here, what you see here is actually a full-blown server. So this is the chassis of the blade itself. The whole idea is these are actually single servers that you can plug in. So you can buy this chassis and all the connectivity is at the back over here. So this will have multiple power supplies. Usually we'll have minimum 2, sometimes even 4 power supplies. It may have, for example, Ethernet ports, which is equivalent to the number of servers you see here, or you may have an inbuilt switch over here at the back. So basically all these will connect to a switch at the back, which will have its own midplane and maybe have 4 uplink ports, which is really good because then you don't have to have, like in this particular case, we have 1, 2, 3, 4, 5, 6. We have 20 servers in here. So instead of having 20 Ethernet ports required, everything could be aggregated through 4 Ethernet ports. And those Ethernet ports could be, for example, 10 gig ports, right? So it give you very, very fast speeds, and maybe the new ones will have 40 gigs per second, right? So really, really fast speeds and very efficient design. So the good thing is once you rack this blade chassis, what is called the blade chassis, into the rack, that means you can plug in servers whenever you need to. If there's an issue, you can plug out the servers and replace them very easily, right? So once the wiring is done, everything is ready. You can just buy the blades themselves, right? So you can buy these components, which are actual servers, the blade servers themselves, into in here, and this is the chassis in which they plug into. So this will ensure that your investment is well worth well used, and that you're kind of trying to optimize the number of port requirements in terms of even power supplies, because here you may have 2 or maybe 4 power supplies. You don't need 20 power supplies in here, or 40 power supplies if you needed redundancy, for example, right? So, and same thing with the Ethernet cabling, as I mentioned. Some of them come with good, like for example, Cisco switches in here that have very powerful specs. So this is a great option to look into. From a connectivity standpoint, if we look here, this is one more slide here before we end for today's lecture, is that you can see the blade chassis, you can see the blade server. Usually it will have multiple ports, as I mentioned. So even here at the back, and this could be a switch, as I mentioned, right? So all these servers will connect to the switch here, and then they can be uplinked to the rest of the network. So instead of plugging into one switch, you can see the switch ports are connected to 2 different switches. So for example, if one switch goes down, then the other switch will still remain functional. Okay, so that's it for today. We'll continue next time. Have a great day. Please take care.